Hello, my name is Brittany Lopez Barreto, and here is my research studying about the effects wildfire have on cyanobacteria in California lakes and reservoirs. Cyanobacteria blooms that harm people, animals, or the environment are called cyanobacteria harmful algal blooms, or CHABs. Some CHABs produce toxins called cyanotoxins, and some common ones are indicated by the EPA shown in the table on the top right. Cyanotoxins are among the most powerful natural poisons known, and unfortunately, there are no remedies to counteract these effects. You cannot tell if a bloom has toxins simply by looking at it, which makes it that much more important to monitor all types of CHABs and general harmful algal blooms. The initial storms after a fire event generally create the greatest post-precipitation runoff and erosion. Sediment transport are the highest the first 2 years post-fire until vegetation recovers. So for now, my study will look at water quality effects within 2 years after a fire. With increased runoff, especially with fine sediment, since this is what travels the easiest, we may expect to see increased nutrient input in nearby water bodies, inducing eutrophication. Satellite imagery estimates the abundance of cyanobacteria by measuring the absorption of light by chlorophyll and phycocyanin, which is an accessory pigment in photosynthesis specific to cyanobacteria. Medium resolution imaging spectrometer, also known as Merced, and Sentinel-3's ocean and land color instrument are able to estimate the average cyanobacteria abundance in the upper 1 meter of the water column for pixels with a spatial resolution of 300 meters. I am also using other satellites such as Landsat 8 and Sentinel-2 that have a higher spatial resolution compared to Sentinel-3, which can be compared above. However, while Landsat 8 provides the spatial resolution to view more lakes, it doesn't provide the spectral resolution to specifically detect cyanobacteria, so turbidity, total suspended sediment, and chlorophyll A will be studied using these satellites. In order to validate my work with all sensors, I need to acquire in situ validation data in order to help increase the accuracy of my results. So ground-collected water quality data is imperative for my study, ranging from a wide area range. Fire information such as frequency and area were provided by CAL FIRE, while the Level 4 Remote Sensing Cyano Index rasters were from the San Francisco Institute and the Aquatic Science Center, also known as SFEI. This graph shows the amount of blooms per lake found for each year versus the amount of acres burned by thousands, where the darkest points are the earlier study years and the brightest shown in yellow are the most recent water years. Each graph separated the land cover class of the watershed each lake resides in. As can be shown, most of the resolvable lakes are shown to be in areas that do not have much development or have some form of vegetation. The few points that are found within these areas, however, do not show any correlation against both variables. The other NLCD classes that have more data and variability appear to be scattered, indicating that if there is a relationship, it might not be strong. However, it is now being plotted against fire frequency for each lake's corresponding watershed. One possible explanation is that more frequent fires lead to more ash and contaminants that settle in the lakes and reservoirs. Frequent fires would also lead to an absence of vegetation in the watershed that can disrupt interception and increase erosion and runoff, leading to algal blooms. Also to note that the loss of riparian shade can also make lake temperatures increase, which also helps the likeliness of CHABs. These are all possibilities, however in reality this has to be looked at and interpreted better with other variables such as fire intensity and/or severity. Here are the results of a non-parametric Mann-Kendall's test, testing to see if the median cyanobacteria index, fire frequency, and acres burned follow a monotonic trend for northern, central, and southern California, and California as a whole. The separation of regions and the methods are based from a method for examining temporal changes in cyanobacterial harmful algal bloom spatial extent using satellite remote sensing by Equihart et al., who used the same Merced satellite for 2008 to 2012. They found that the spatial extent of CHABs were the greatest in Central California for all risk types for blooms, while Northern California had a decreasing spatial coverage for areas at high risk. My analysis looks at the median cyanobacteria index value rather than spatial extent, along with a greater year range, which can lead to differing results. For median cyanobacteria index, all of 2016 to 2020 appear to not follow a monotonic trend, stating the values vary for this period, and a way to explain this is due to the small number of years used. For 2002 to 2012, however, we can see that all appear to have a monotonic trend and appear to be increasing. For fire frequency and acres burned, all appear to be varied, leading to no one-direction trend, with which the exception of Central California for 2002 to 2012. The median Cyanobacteria index results for this region and time period had the lowest tau value, which might be explained with the higher fire frequency. A high fire frequency normally leads to less intense or severe fires from occurring. The integration of further fire characteristics can help understand and interpret these results further. I plan to integrate more fire characteristics along with looking at sites on a watershed by watershed basis for further comparison. I currently am in the works of compiling in situ data to relate them back to my remote sensing products. If you have any data or know places where I am able to access site collected water samples or samples collected by installed instrumentation and are willing to share, please message me in the email shown in the slide and it would be greatly appreciated. Thank you for watching my presentation.